Hello, this is Kris Covey from 3VGeomatics. Today I'll be presenting satellite-based InSAR for operational monitoring of ground displacement across oil and gas networks in the Appalachia. I'd like to thank everyone for attending and EnerGIS for their conference. So quickly about 3VGeomatics. So we are based out of Vancouver, British Columbia. We've been in operation since 2007. We have 50 plus employees and we are 100% InSAR focused, so that's all that we do. We've had significant growth year over year. We are satellite independent, so we use the best SAR satellites for each individual project. We customize our scopes of work based on clients' areas of interest, levels of vegetation, frequency of monitoring requirements. And InSAR is a proven technology. We're delivering over 2,000 plus reports per year with no geographical restrictions. So we're delivering reports in up to 40 plus countries with reports being generated every day of the year. So why InSAR? So InSAR's key advantage is that it is remote. We don't require any kind of infrastructure on the ground. So everything is done via satellite. Our areas of coverage are massive. We're generating millions of data points of potential displacement. The level of vertical displacement we can detect is anywhere from millimeter to centimeter precision. We have frequent revisits. Every 4 to 14 days, we can take a new image over a site. So what we're using this for in the Appalachia is for detecting unknown geohazards along pipeline corridors and tracking known geohazards for any kind of acceleration. So InSAR uses radar satellite images taken over time to measure ground and structure displacement. So what we start with is a SAR image, which is illustrated on the left-hand side. We build up a stack of 6 images and produce what's called an interferogram. We process the interferogram, and if you see on the right-hand side here, our end product shows any kind of displacement highlighted in red or blue, with red indicative of moving towards the satellite and blue, or sorry, red indicative of moving away from the satellite and blue moving towards the satellite. So our area coverage contingent on the satellite used is anywhere from 600 to 18,000 square miles. Our data density at 25 centimeter resolution, we can generate up to 100,000 data points per square mile. In urban areas or non-vegetated areas, we can detect as little as 2 to 3 millimeters of motion. And again, our frequency of revisit is every 4 to 14 days. So this is how InSAR works. So as a SAR satellite orbits over an area of interest, it emits a pulse of radar waves with a known wavelength towards the Earth. This phase information is recorded each time a SAR image is acquired. So what we do is we measure the difference in each phase for each pixel. Between each image is the amount of displacement measured for that time period. So essentially, once we've got that stack of images, we can show you how much it's moved over the phase of the time. So the key advantages with radar, so why are we using radar images? Well, it works at night. It can penetrate cloud cover. We're at 98% reliability of acquiring images that are usable, and it's ideal for measuring precise changes over time. So in the last 30 years, so InSAR was started in the early 90s in the academic world, but it's been largely adopted in monitoring mining sites and pipeline corridors over the last 5 years. Really what's generated this extra capabilities are the advancements in processing software, cloud storage, faster processing times, more satellites with better resolution, and a key factor has been the reduction of cost of the images. Some images are even free nowadays. So essentially, this has led to us delivering faster reports that provide actionable intelligence and provide operational decision-making based on InSAR ground displacement results. So in 2017, we worked on a project with a large pipeline operator, the largest in North America, and an engineering firm. Essentially, the project was to determine what applications InSAR can be used for monitoring pipelines. So it was determined that we can identify landslides and other network or other areas of displacement along pipeline networks, including subsidence and heave. So essentially in 2020, pipeline operators have now incorporated using InSAR to monitor their pipeline corridors for ground movement to coordinate inspections. We can also identify critical locations to use other means of monitoring, including strain gauges or inclinometers. So our data is being used to verify and align ground movement with the other data sources. Essentially, we're improving effectiveness of landslide mitigation practices, and our historic archive data can also be used to route new pipeline construction. So this is what the reporting looks like. So essentially, once we've got 6 to 12 images acquired, we can generate what's called an interim displacement report. So essentially, as you can see on the image on the left, that is the black is the center line. The yellow is the areas that aren't moving, and the blue and red are the areas that are moving. So we automatically generate contours that indicate any kind of ground movement that can affect the integrity of the pipe. Once we've got 13 plus images, we can provide what's called a comprehensive displacement report. So that again is a heat map of the pipeline corridor. However, now we've got a time series which you can click on each data point showing you movement over time in a chart. So what we use now, we use signal to noise contours. So these are automatically generated. They identify any kind of areas of significant displacement within a certain buffer of the infrastructure. So what it does is it's the measurement of the signal to noise. We provide 3 different thresholds with our contours as SNR 4 being the strongest evidence of displacement, 3 being reasonable, and 2 being weak. As we acquire more images, the 2 sigma levels may increase as the noise reduces, as the InSAR results get better once we have more images. We've also incorporated tools that measure the distance to the right-of-way and also the size of the actual contour of displacement. So what we're going to talk about for the work in the Appalachia is ALOS-2. It's a Japanese space agency satellite. It's got an L-band, which is a longer wavelength that can penetrate the vegetative cover. As we know, the Appalachia is highly vegetated. And the resolution, so we get pixel points every 3 meters. So as we can see, the key applications for using ALOS-2 are vegetated pipeline right-of-ways, oil wells, slopes, and levees. And there are other options for satellites, but those are typically used in urban or non-vegetated areas. So I'm just going to go over resolution, which is a key factor to determine the displacement area. As you can see, the optical image on the left shows cracking of a known landslide that we were given by a satellite operator, or sorry, a pipeline operator. Our year 1 of the program, we used Sentinel 20-meter resolution. The area isn't highly vegetated. However, as you can see in the image in the middle, that we didn't notice any kind of displacement. The resolution was too coarse to identify such a small landslide. So in year 2 of the program, we switched to ALOS-2 at 3-meter resolution. We're able to identify a 680 square meter landslide. So a key factor when developing a program to monitor pipelines is both the level of vegetation and the size of the landslides we're concerned of. So now we'll get into the work we are doing in the Appalachia. So indicated by the image on the right, you can see all the pipelines available through the EIA Centerlines public portal. And the 9 different footprints we are monitoring the Appalachia for pipeline operators in 2020. So we're covering over 12,000 square miles. Within those 12,000 square miles, there's over 10,000 miles of oil and gas pipelines, well sites, other types of infrastructure. So what we're doing is we're using InSAR to monitor ground displacement on an ongoing basis. And we're delivering actionable reports during peak ground displacement seasons after rainfall events and over the course of the yearly monitoring program. So why are we doing this in the Appalachia? Well, as you can see here, the USGS landslide susceptibility map with the center lines identified. These pipelines are in the highest prone area in the US for landslides. You can see that these footprints are, high and deep red, indicating that these areas are highly prone to landslides. And over the course of the last 5 years, there's been 8 or 9 pipelines that ruptured due to landslides in this area. So several did cause explosions leading to loss of life. So any kind of means to monitor these pipelines from space has been a big uptake over the last few years. So here's how InSAR is used in project operation. So essentially we generate results. These contours are then measured from the distance to the right-of-way. If they are intersecting or close to the right-of-way, the pipeline operators have a program they institute to do field verifications or to identify if this is a concern for the right-of-way. So here's an example of some of the work we have done in the Appalachia. So this area here is red, so it indicates that it's moving away from the satellite. Sorry, it's in blue, so it's moving away from towards the satellite. at 12.8 centimeters per year. And as you can see, the black line is the pipeline right away. So we've provided this information to the pipeline operator, and then they determine what to do next. Here's an opposite type signal. So this one here is in red, so it's moving away from the satellite. The key concern here, though, is that it's very close to the right of way, and also it's been stable from July to March of 2020, didn't show any kind of displacement, and then a big acceleration from March of 2020 to May of 2020, indicating that this area has moved 15.6 centimeters away from the satellite. So that's moving down the slope. So may have been a rainfall event or whatnot, but this is definitely an area of concern that we've generated for the pipeline operator. So here's an example of some of the ground verification we've had from our results. So on the InSAR generated results are in the top left-hand corner. Red is indicative of moving away from the satellite and down the slope. So we've got the field verifications where we provided this data to the pipeline operator. Definitely a high consequence area, as this is a North Saskatchewan river, which is a water body. So some more results we generated in the Appalachia where we've got some ground truthing. So here's an area that was unknown to the pipeline operator, indicated in white on the left-hand side. So we provided these details. The operator then checked their strain data from their ILI run, and it coincided with some strain on the pipe, which is most likely caused by ground movement in the area. Another result here, we had a historic landslide that the operator thought was not currently moving, but we identified ground creep along that slope. They actually went in and mitigated this area. With figure 5 on the right-hand side, the operator had a confirmed class 3 landslide they were monitoring with GPS survey, and InSAR picked it up that was still moving as well. And the other means to do verifications is comparing LiDAR differencing versus InSAR. So we've got our InSAR results indicated in yellow, and then our LiDAR differencing in blue. It's not exactly the same time frame, but you'll see great parity between the data sets of us showing movement and LiDAR differencing also identifying movement in the same areas. So another example here is that there's longwall mining activity near several right-of-ways south of Canton, Ohio. If you see it on the left-hand picture, we've got an area of movement we identified in 2019 in August. September, we show that it's moving from west to east. And then further in October, it's moving from west to east. So we can clearly see that longwall mining activity moving along as they continue that activity. Of course, the pipeline operators are aware of that activity and do take precautions with the pipe. So the future of L-band, so InSAR monitoring, we really anticipate that we're going to be monitoring all of North America at some point. InSAR is launching. It's a NASA-based satellite. Anticipated launch date is sometime in 2021. It's a new satellite. It will be L-band, so it can penetrate vegetative cover to measure ground movement below. The key factor, though, is we'll have a little coarser resolution at 6 to 8 meters. But some of the advantages are imaging the entire Earth every 12 days. The images are free, so definitely will reduce some of the cost. And the other one launching by the Japanese Space Agency sometime, hopefully March of this year, is ALOS-4. So it's the successor to ALOS-2, which we are currently using in the Appalachia. It will be compatible with our current data. And again, we'll have that higher resolution. But one of the key advantages is that the swath width will go from 70 kilometers to 200 kilometers. So we're going to get very large areas in one footprint. So hopefully that will launch in March of 2021. And we can continue on with the data sets, just much larger data sets. So that is the presentation. If you have any questions, I put my email address and also my phone number. Thank you.